Net ionic equations. When you do net ionic equation, the first you want to do is like figure out what kind of reactions occurring. So your options are either acid-base, precipitation, redox, or other. So we're going to call this APRO. A P R O, the APRO method. And the reason is the most common reactions you'll see on the AP exam is either acid-base or redox. P is in the middle because you want to look for it before you look for redox. It's just one of those patterns. O is for other. That's a vast category. These are the questions that will give you a little bit more of a challenge, and I just lump them in all together so I don't have too many letters in the sequence. So it's APRO and not APRO, LIDO, or something else. So the first reaction we're going to look at is magnesium metal is burned in nitrogen gas. So you want to start out by writing out what you think the reaction is. The question says magnesium metal. That tells you have a solid. That also tells you do not put a charge. So please don't put Mg2 plus because it didn't say magnesium ion and it did not say solution. It is burned in nitrogen gas. Alright, so what kind of reaction is this? Well, first off, we know that we can't eliminate anything from the reactant side because you have a solid and you have a gas, two things that cannot be eliminated. So we're going to look through our list. Is this acid-base? Well, there's no acid. There's no sign of a base, so that's out. It's precipitation. You have no solutions, so that's out. Is it redox? Actually, it turns out it probably is. And the way you could usually identify redox is that you have a diatomic molecule because those love to change charges. So the charge on this is 0. It's elemental state. Magnesium is also 0, elemental state. So should you write Mg2 plus and N3 minus? No, because you can't get a solid and gas together and produce ions. Ions are only produced in solution, means you need water. So what's another way I could change the charges? I can combine them. So if you combine them, do your good old-fashioned crisscross, you get Mg3 and 2. Magnesium is a positive 2, that's why it's N2. And nitride is a negative 3, that's why it's 3. Notice the charge now, plus 2, minus 3. We went from 0 to positive 2, that's oxidation. Went to 0 to negative 3, that's reduction. So this would be redox. So we're going to put redox right there. All right, let's look at the next reaction. You have sulfur dioxide gas. Okay, it means you can't get rid of it. Is passed over solid calcium oxide. All right, we have a solid, we have a gas. That means, guess what? Nothing can be eliminated. Also means you have no water, so that means you can't have ions on the product side. You could have ionic compounds, but you can't just have little ions floating around. So what can you do here? Well, if you look at it, it's not acid-base, it's not precipitation, it's not redox, so that means it's other. So what do you do with the other category? Well, this is kind of trial and error. As you get more practice over this, you start picking up things. But typically what happens when you react a solid with a gas, what ends up happening is you combine all the elements. So this becomes CaSO3. Notice there's three oxygens, one sulfur, one calcium. So this is the other. See, a little bit more challenging. All right, let's look at the next reaction. We have lead foil. So that's Pb. Foil just means you have a solid. It's immersed in silver nitrate solution. There's a key word, solution. When you see solution, that's your way of saying, or that's the AP's way of saying that you have ions. Break these apart. And what else I'm going to do right off the bat is I'm going to look at which ions I have. I have silver and I have nitrate. Nitrate is never involved. So guess what? I'm going to get rid of it. I'm not even going to put it into the reaction. I'm just going to put silver. And because it's in solution, that means you need a charge. Here, not a charge because it's a solid. Here, a charge because you have an ion. All right, so what do you do now? Well, look at the possibilities. Obviously not acid-base, not precipitation, so can it be redox? When you have two transition metals, you will have redox. Guess what? You have two transition metals. So what does that mean in the situation? Well, here lead is a 0, silver is a positive 1. So which one of these will be oxidized? Well, you really don't have many choices because silver cannot become more positive, and lead definitely can't become any more negative. So that means the lead has to be oxidized and silver has to be reduced. So that's what I'm going to do. Put lead at its next possible charge. Now lead can be positive 2 or positive 4. I'm going to go with 2. And typically you go with the lower possible charge. Now silver, what are the options for silver? It could only become more negative, which means you just become solid silver. So this redox. You notice we have had 2 redox reactions already. Alright, so let's go down and do a couple more. Alright, now we're going to look at ammonium sulfate. This is a saturated solution of barium hydroxide. So you see how the word solution is written twice here? Well, that's good news for us. That means we have to break apart everything. This is saturated solution. This basically means that you have a solution that's basically the maximum amount of solid that's possible there. Not that important, but we're still going to underline it for now. So ammonium sulfate. Now, you could write ammonium and sulfate, and I'm going to do that because sometimes ammonium can actually be involved in an acid-base reaction. So ammonium you don't get rid of like you do nitrate. Even though ammonium typically is soluble, you still want to write it in. Sulfate is SO4, 2 minus, is added to saturated solution of barium hydroxide. So that's Ba2 plus OH minus. Alright, so what can we do? Alright, this is acid-base. Well, as I mentioned earlier, ammonium sometimes involved in acid-base reactions. So whenever you have ammonium, look for acid-base. So this is obviously the donator because of the acid. So can you find anything here that can accept an H? Well, there you go, hydroxide. Hydroxide's a base. So that's what we're going to do. We're going to donate a hydrogen from ammonium. That leaves us with NH3 because we lost an H. And OH gained an H, so it becomes H2O. So there's the acid-base portion. You notice I only exchange a single hydrogen. What most commonly happens with some students, they start getting rid of more than one hydrogen. Don't do that. Acid-base, just give one H to the base, you're done. Now, the barium sulfate. Typically, acid-base with solutions can also have a precipitation reaction. So you have to double check to make sure that the 2 things that are left cannot form a solid. Sulfate, barium, can they form a solid? Turns out, yes, they can. If you look at your solubility rules, that you'll know that barium sulfate actually is a solid. So here we have both acid-base and we have redox. That can happen. Alright, acetic acid solutions add to solution of sodium hydrogen carbonate. So acetic acid, it's a weak acid, so we do not break it apart. Strong acids, you dissociate. Weak acids, you do not. So you have to memorize your 7 strong acids and understand that everything else cannot be broken apart. Solution of sodium hydrogen carbonate. Now you notice the solution here too, so you would think that you break it apart. Not in this situation. With acid bases, even if they say the word solution, still try to figure out if it's a strong or weak acid and then break it apart if you need to. Alright, sodium hydrogen carbonate. What do we write for this? Well, we have Na plus and we have HCO3 minus. My habit is always get rid of what you don't need. Is sodium going to be involved in this reaction at all? Most group 1 elements are never involved. So I'm going to kick it out. The only time I include group 1 elements if it says solid. So here it doesn't say solid, so goodbye sodium. So now we're left with HCO3 minus. This way, even if you have no idea what the products are, you still get a point for the reactants. Alright, so now what are the products? This has to be acid-base because you have an acid. And you also have something here that can accept an H, which is sodium hydrogen carbonate or just hydrogen carbonate. So what I'm going to do is take an H from acetic acid and donate to HCO3. That gives us C2H3O2 minus plus H2CO3. Now here's a trick with this. Carbonic acid never stays as carbonic acid. It always breaks apart into CO2 plus H2O. So when you're doing this kind of reaction, you're going to have to basically break it apart and this just goes away. So you have with CO2 plus H2O. You have to remember to do that. Alright, let's do a couple more questions to see if we understand the concept. So we're going to go up here and we're going to do the one involving potassium iodide and potassium iodate. Alright, solutions of potassium iodide. There's the key word, solutions. So what do? I know I can break them apart. Now potassium, like I said, group 1, if it's a solution, just get rid of it and make your life easier. So I'm just going to write I minus. And potassium iodate. Once again, goodbye potassium. So iodate is just IO3 minus. So what kind of reaction can this possibly be? Well, is it acid-base? Well, you have the word acidified, and I almost forgot all about that, so let's put that in. Whenever they say mix an acid solution or acidified, you add H+. That's important because whenever you see the word acidified or H+, you are guaranteed redox every single time. So anytime you see 3 reactants, and one of them being H+, it's redox automatically. So how do you handle this? Well, if you look at it, you have a diatomic. Remember, those love to be oxidized and reduced. So what can I do to show it? Well, I minus is a -1 charge, and in here you have IO3. So let's figure out the charge inside of here. We know O is overall charge of -6. So individually, each O has a charge of -2. On top, I always write the overall charge, and on the bottom, I write the individual charge. And I start with the element I know the charge is for, and O is one of those. All right, now I, because the overall charge is -1, you do not make this into +6. You actually make this into +5. So individually, it's +5. So you have -1 and +5. What do? Well, I know I minus turning to I2 with a 0 charge would show me oxidation. You're going from -1 to 0. That's becoming more positive. That's oxidation. But guess what? Going from +5 to 0 is also reduction. So it's a 2 for 1. This is actually oxidation reduction. You can actually have 2 reactants oxidize and reduce to the same product. So that leaves us with H+. What are we doing with that? Here's the rule. If you have H and O floating around, put them together. Also for redox, you always have H2O as a product when it's acidified. It's just one of those things. So this was redox. All right, dilute sulfuric acid. Now you have what's called a strong acid. And guess what? You have to break it apart. You cannot keep it as H2SO4 because you'd be wrong. It's add to solid calcium fluoride. That word solid means you cannot break it apart. You have to keep it together. So what are the possible reactions? We have an acid, we have a solid. Well, first I'm going to look is for acid-base reaction. Strong acids are always involved in acid-base reactions. So is there anything here that can accept an H? Fluorine can. Negative ions can typically accept H's. So anytime you have a negative polyatomic ion or negative ion, that's what's going to accept your H. So I'm going to have one of my products as HF. All right, plus. Now look at your options. You have calcium and sulfate left. You have to show calcium on the product side because it's a solid here. And on this side, it's going to be an ion. So what do? Look for precipitation. Remember, acid-base with precipitation is very common. So this actually becomes CaSO4. So you have both. You have both precipitation and acid-base again. So acid-base with precipitation. All right, now let's look at this one. Solid ammonium carbonate. Solid's telling you Don't break it apart. CO3. Now, this is heated. A lot of times students confuse heated with the presence of oxygen, which is burning. This is not burning. Heating always tells you you're having decomposition. And with decomposition, you're going to break everything to its elemental parts. So you're going to look at this and ask yourself, what can an NH4 break apart into? Well, it could break apart into an H2, or it could break apart to NH3. Which one's more likely? Every time for this, it's going to be NH3. So we've counted for the ends. What do we have left? Well, we have C, and we have O. So you can actually produce CO2. And because you're having a decomposition of this particular type of product and there's H and O floating around, you're also going to produce H2O. So that's your decomposition. All right, and the last one we're going to go over is hydrogen peroxide. That's H2O2 is added to an acidified solution. Remember, acidified means H plus of sodium bromide. Solution is telling you you're going to break it apart. Sodium, goodbye. All right, so now look at this and ask yourself what is going to happen. Remember, whenever we have this acidified, we know guaranteed redox. So we're going to put redox up here. We just know it's going to happen. So what did I say about bromine and all the diatomics? They love to get involved in redox. So to account for the oxidation, I'm going to put Br2. So I'm going to go from -1 to 0. So you've covered oxidation. Now you have to cover reduction. So how am I going to do that? Well, first I'm going to do is I have H and O floating around. So I'm just going to put H2O. Why? Because I know that this always produces H2O. Now look at it. O here, it's peroxide. So it's actually a -1 charge. And hydrogen is +1. H, +1, that's not going to be what's going to be reduced. So you have to find something else to be reduced because you already have your oxidation. That leaves you with only O. Well, if you put H2O, guess what? You have -2, and there is your reduction. And that's how you would do net ionic for these types of questions.